Lesson 14.7 is about something called binomial distributions and probability. So we're going to look at some situations that up until now we've just been unable to solve with the probability formulas that we've learned. And the context for these first few examples are an NCAA Final Four matchup between Auburn and Virginia that took place in 2019. And in this game, Kyle Guy from Virginia was fouled while attempting a three-pointer at the buzzer. He missed the shot and therefore headed to the line for three foul shots. And at that point in the game, with only 6/10 of a second left, Auburn was winning by 2 points. Now, we're going to watch a video clip of the end of the game and kind of break it into chunks, and we're going to calculate some probabilities as we go. So, one other piece of information that you need to know is that Guy's career free throw percentage is 82%. So, he's a good free throw shooter, and we're going to assume that that number, 82%, represents his ability and that each shot is independent. So, the probability of him making a free throw is going to stay 0.82 for each shot. So, we're going to watch just a little bit of the end of the game before we do any probability calculations.
Dangerous guy is the inbounder, but I don't think they have enough time to give it back.
Got a 6'11" man guarding the inbounds pass, and Wiley. So here we go. Jerome to inbound.
They got the lob.
Looking. It's Guy from the corner for the win. Hold on. Did I hear a whistle?
Wow.
We got a foul call. Wow. The Auburn fans thought it was over, but there was a whistle.
Dangerous guy is the inbounder.
Now, notice at that point in the game, it looked like the clock had run out, but the referees end up putting 6/10 of a second back on the clock in order to give the player time to shoot his free throws. So remember, they're down by 2 points, right? And he gets 3 free throw attempts. So let's look at the possible scenarios here. First of all, they could win the game if he makes all 3 of those shots, because currently they're down by 2 points, right? The score is 60-62. So we're going to use H for hit the shots, and that's the only way they can win the game at this point. Now, if he misses all 3 shots, they're going to, of course, lose the game. But there's another way that they could lose the game. It's possible, for instance, that he might make the first shot, but then miss the last 2, and that would make them lose by 1 point. However, he might miss the first one, hit the second one, and then miss the third, or he might miss the first 2 and make the third. Either way, all of those scenarios will result in a loss. So there really are kind of 4 different ways that they could lose this game at this point. Because they're down by 2 to go into overtime, he would have to make 2 of the 3 remaining free throw shots. But they could be in any order. So he could, for instance, hit the first 2 and miss the third one. Or he could hit one, then miss one, and then hit the last one. Or he might miss the first one and then hit the last 2. And we're going to calculate the probability of each of these different events happening. Well, the chance of them winning the game, if he hits all 3 shots, would just be 0.82 times 0.82 times 0.82, or 0.82 to the third power. And that would give us a probability of about 55%. And I'm doing quite a bit of rounding here, more than we'll typically do, just for the sake of keeping it simple for this first example. Now, the probability that they lose the game, we have to do a little bit more work for this one. First of all, he could miss all 3 shots, which would be 0.18 to the third power, and that's about 1%. Now, for the other calculations, hit, miss, and miss, they're going to require you to multiply 0.82 times 0.18 times 0.18. And all 3 of those different scenarios involve those same numbers in the product, just in different orders. So to simplify, I'm going to do 0.82 for the 1 hit and 0.18 squared for the 2 misses. And because we have to essentially repeat that 3 times, I'm just going to multiply that result by 3. And that will give me a probability of 8%. So the total probability that they lose the game is going to be 9%, because we had 1% up above and then the 8% that we just calculated. Now, the last scenario is that they go to overtime. And here he has to hit 2 and then miss 1. So hitting 2 would be 0.82 times 0.82. Missing 1 would be 0.18. And we can multiply those in any order. So I'm going to just simplify that using some powers. And then because there are 3 different ways for that to happen, we'll put that coefficient of 3 out in front. And that gives us a total probability of about 36%. So notice if we add 55, 9, and 36, we get a total of 100%. Now let's watch his first shot and see what happens.
tell you, if you're Virginia, this is the guy you want on the line. Your first team all ACC player.
81%.
All right, so we know he made the first shot. The score is now 61-62, so they're down by 1 point. In order for them to win, he has to make the 2 shots that he has remaining. So he has to hit the next 2. To lose, he either can miss the next 2 shots, because then they would lose the game by 1, or they can go to overtime. And an overtime situation means that he would have to hit one of the 2 remaining shots that he has left. So either hit the next one and miss the last one, or miss the next one and hit the last one. And like we did in the first box, we can calculate those probabilities pretty easily. Hit and hit would be 0.82 squared, which is about 67%. Miss and miss would be 0.18 squared, which is about 4%. Now, hit and miss, we need to multiply 0.82 times 0.18. And there are 2 different ways that that can happen. So I'm going to multiply that together and then multiply by 2. And that would give us a probability of about 30%. Now, notice here, if I add together 67, 4, and 30, I am actually at about 101%. And that's round off error. It doesn't mean that we rounded wrong. It just means that because we rounded up in more cases than we rounded down, our percentages worked out to be a little too high, but that's okay. Now let's look at the last shot, or the second shot rather.
He's tied it. Wow, this is unbelievable.
All right, now at this point in the game is tied, right? He made the second shot. So really now the only options are that they could win the game if he makes the first or the next shot, or they could go to overtime if he misses it. So now their chance of losing the game is actually 0%. So to go to overtime, he would have to miss the next shot. And the probability of that happening, of course, would be 18%. And to win, he has to hit the next shot. And the probability of that, of course, is 82%. Let's see what happens.
He got all 3. Hutchins.
Now you got it.
Here we go. 0.6 seconds.
Nobody on the inbounder.
Durafoy's going to go to the other side. He's got Brown all the way in the far court. Might as well heave it all the way the distance. A Grant Hill pass. Here it is. Brown turns around. It's off the mark. And Virginia is heading to its first ever.
All right, so we see that they ended up winning the game. Now, this scenario is very similar to some other ones. For example, if you toss a coin 5 times and you count the number of heads that occur, or if you're putting a ball 18 times and you record the number of times that the putt lands in the hole, or if you're taking a quiz that has 10 multiple choice questions, each with 5 answer choices, and you want to count the number of questions that you have correctly. In all of those cases, we have kind of 4 things that are happening. And when those 4 things happen, we consider this to be a binomial situation. So thing number 1 is that the possible outcomes for each trial can be classified as either success or failure. For the free throws, it's pretty easy to determine what success and failure means. When you're tossing a coin, you can decide heads is success, tails is failure. Or if you're answering questions on a multiple choice quiz, even though there are 5 answer choices, only 1 answer is right and the other 4 are wrong. Second thing that has to be true is that your trials must be independent. So the first trial does not affect the second or the third or any subsequent trial. Third, the number of trials, n, must be fixed in advance. So we know how many free throws we're shooting. We know how many times we're tossing a coin. And lastly, on every trial, the probability of success must be the same. Now, when all of these conditions are satisfied, you have what's called a binomial probability situation. And so you can use the binomial probability formula. And we're going to kind of spell out what all the different parts of this formula represent, because it looks a little bit complicated, but it's really actually pretty easy to use. If we want to calculate the probability of getting exactly k number of successes, then we would do a combination, n-c-k, multiply that by p to the power of k, and then 1 minus p to the power of n minus k. Okay, so let's break that down. P is the probability of success. So in our free throw example, that would be the 0.82. 1 minus p, therefore, is the probability of failure. This exponent k represents the number of successes. This exponent over here, n minus k, represents the number of failures. And notice if you add k plus n minus k, you get n, and n is the total number of trials. So the number of successes and the number of failures has to equal the total number of trials. Now, the combination out in front is just telling us how many different arrangements we could have of successes and failures. So when we did the free throw example at the beginning, we were able to count those because there was a small number. But sometimes we have a large number of those, and rather than spending our time counting them, we just use combinations to help us figure those out. All right, the next video for this lesson will walk you through the examples.